Hey everyone, my name is Rithik. I'm going to be going over the graphs question in the CSM final review 61B worksheet. So let's dive right in. 4.1, state if the following statements are true or false and justify. For all graphs, assume that edge weights are positive and distinct unless otherwise stated. So the goal of this question is to really understand graph algorithm concepts and go over some manipulations which allow us to solidify our understanding of them. So this is a really important question, and often a lot of exam questions show up that are similar to these. So part A, adding some positive constant k to every edge weight does not change the shortest path tree from vertex S. So the best way to show whether something is true or false is trying to find a counterexample, because if you can find a counterexample, that immediately nullifies the statement and makes it false. So fortunately, they give us this little example here. So let's just first look at this without having to add that constant k. So let's look at this path first, A to C. To clarify, A is our starting point, C is our goal. So from A to C, we can see that the path would be 5, whereas the path from A, B, C would be 1 plus 2, which is equal to 3. So just from this, we can see the shortest path would be from A, B, C. Now, let's try adding a constant k. And they actually gave us a constant to use as well. So let's try that. Let's erase all of this. So I'm going to add 5 plus 2 is equal to 7, plus 2 is equal to 3, plus 2 is equal to 4. Now the path from A to C would be 7, and the path from A, B, C is also equal to 7. So that means that we could ultimately produce A to C directly, and that would be a completely valid shortest path after adding k. So here's a problem. With Dijkstra's, well, let's first, this is false because we found a counterexample. And the problem is when we're trying to find a shortest paths consist of us trying to find the total sum of edge weights to get to the point that we want to get to. And because of that, every single time we're passing an edge and we're adding a manipulation, that manipulation gets compounded. So in this example, to just show a little bit more mathematically, so AC originally was 5, and we're adding a k value. Then the other one from A to B and then B to C was 1 plus 2. And then now, instead of adding just k, we're adding 2k because we had 2 different edges. So now if you were to compare that, so in this case, we're trying to see which one would be less than or equal to. So we can do k plus 5 is less than or equal to 3 plus 2k. And then let's move k to this side. So k is greater than or equal to 2. So that means that any value which k is greater than 2 would make AC the better edge, the better path to get to C. Whereas if it's less than that, k is less than 2, that would mean that ABC is the best possible path. So this is kind of a little bit more rigorous proof. All you need to show is that there's a counterexample here, and that should help you understand why this question is false. So let's move on to the next question. The next part is doubling every edge weight does not change the shortest path tree. So this one might be a little bit confusing because I just said, oh, if we add something, it could be a different path. However, it is a little different story when we come to doubling them. And let's actually use the same example. So I'm going to erase all of these ones. Let's cut that. And let's use the same k value that we've used. So originally, it would be ABC, same story. Now let's try doubling them. So this would be 10. Let me actually change the color so it's easier to see. 10, 2, and 4. So now it's 10 if you go from A to C, and then it's 6 if you want to go A, B, C. All right, so now we still have A, B, C as our path. That means we haven't really found a counterexample yet. But the thing that's important to notice is that even if we multiply them, there's still an equal factor. Each point is still an equal factor away from our starting point. So what that means is that if I erase these values, so C from A, let's consider, let's use actually our k value like mathematical understanding again. So let's say 5k versus, we can say k plus 2k for the A, B, C path. Now, what we're trying to see is there any way that k can be a value that is less? Well, in this case, we know k is equal to 2. But what the point is that we can show through this that k plus 2k would still be less than 5k. And we can show that as well through math, because this would be 5k is still going to be greater than 3K. So all you need to show for this is something like this. You can say the constant factor bit, whatever makes the most sense to you, but it always helps to use an example just to reaffirm your understanding and prove to you that this statement would be true. Cool. All right, let's move on to the next question. If the weight of each edge is decreased by 1, then the resulting shortest path in any graph from U to V is unchanged. So this one is also a little bit tricky because now we've identified if we add 1 or add 2, I guess in part A, it did change. And the resulting shortest path in any graph, in this case, they're saying would be unchanged if we were to decrease it by 1. Now, at first glance, it would be, I would consider it true, but the important thing to understand is negative edge weights. And there is a possibility that you have a graph that is like this. You could have A, B, and C. Let's say this one's 0, this one is 1. And now if we were to subtract, let me give a better example than that. Actually, this one's fine. So let's say we were to subtract 1 from every single one. Then now we have a negative edge weight. And that could potentially change what your shortest path is. I need to find a better example. I'll think about it a moment. But anyways, what's important to realize is that you could make each edge shorter, but because we're adding some sort of constant, the same story happens as what happened in part A. And let's show that via here. So let's say I subtracted 2. So this would be 3, -1, 0. And now we created the path where, so AB would still be the shortest possible path, but similar to the others, to part A, there's a chance that they compound and ultimately we get a path that is different than what we initially created. So let's show this a little bit more mathematically. So let's say 5 minus some K value, and then we can say 1 plus 2 minus 2K, again, because it compounds, which is different. Remember that SPTs have compounding, whereas MSTs are actually going to be a little bit of a different story, but we'll go over there once we reach part D. And there's a case, there is a potential possibility where this value would be less than or equal to the other value. And we can just kind of prove that really quickly. K is less than or equal to 3 minus 5, so it's -2. So this is the same actually equation as what we showed here. But what that proves to us is that there is a chance, I guess not really with this one, but there is a chance that you could create an equation which proves to you that the final graph could be different. So this one would be false. Cool. All right, let's go over MST. If a graph G has a unique MST, it must have unique edge weights. So on the right here, I kind of went ahead and wrote an example ahead of time. And let's just use crucifixes. So we're going to start off with the lowest edge weight. So we're going to do 1 right here. Let me switch to yellow. 1 right here. Then 2, I can just pick any of them randomly. So let's choose this one, and let's choose this one. So I've hit every single point. This would be my MST. So now, here's a problem. The question says, if I have a unique MST, I must have unique edge weights. In this case, I do not have a unique MST. I could have also picked this one. But let's look at a different example. Let's say that A, B, C, the only options, this was our total graph, and we're trying to find the MST. This is the only possible graph we can create. Therefore, it is a unique MST, but it does not have unique edge weights. So therefore, the statement is false. But an interesting thing to note is that the converse is true. So let's say that I have unique edge weights. That means that we'd have a unique MST. This is really important to take stock of, because now if I were to have A, B, and C, once again, to use the same example, let's say 3 and 2. And let's say this one would be to D, and this is 1. And this is, let's say, 5. No matter what, you'd only have one option. And that would be the best MST. And the only time that you have multiple options for your MST is when you have an example like this, where you have multiple of the exact same edge weight. Cool. Let's erase that. Just get a little cluttered. Okay. Let's look at the next question. Adding some constant k to every edge weight does not change the minimum spanning tree. Now, this one also, again, similar to the previous questions, but actually is true. And the reason why I'm saying the answer first, because I think it's great to look at this via an example. So let me show this right here. Let's use this example on the right. So let's try adding a k value. I'm going to use the color blue to show that plus k, plus k, plus k, plus k, and plus k. Again, I'm going to run crucibles just like before. I'm saying, okay, 1 plus k is still the minimum one. 2 plus k, I can pick either one. And that would be our final MST. So that's weird. Like, why did this one be the exact same? The reason why is because, and this is really important, I recommend like putting this down in the cheat sheet or something to think about, is MSTs. You can think of them as individual to edges. So like edges are individual or separate, however you can think of it better, whereas SPTs, edges compound. And that's the thing I was mentioning earlier, is that whenever we make a manipulation to an edge, to every single edge, that change will compound because we're looking at the sum. We're looking at the total distance from point A to B, whereas in this case, when we're running crucibles or prims, we're only looking at the specific edge and trying to determine what we should do next. So that's really important because now if I were to add something, it would only change that specific edge for MSTs, whereas for SPTs, it would affect the entire path. So it means that part E would be true. Now let's look at F. F is actually the exact same story. So if this might be a bit harder to erase, but I'm going to erase this. Let's put that 2 back in. And right here, so let's say I want to multiply each one by some constant. So I'm going to say 2k, 2k, 3k, and just k. Same exact story, right? We're going to pick k first, then we pick between the 2k's, and we can end up with the exact same MST. And this would be true. And similar story, because edges are individual, it would not change our total path. Cool, let's move on to part G. This question is a little bit longer, so stay with me. So let S, V minus S, be a specific cut through a graph. If an edge E is not the lightest edge across this cut, it cannot be part of any MST. So let's look at the example on the right. We have A to B and A to C. I'm going to make this cut. We're going to have S on the left and T on the right. And the first thing we're going to do is we're going to find the lightest edge. So we analyzed A to B, which is 1, and A to C, which is 2. So I would pick A to C, A to B, excuse me. And then after that, we would continue and we would create a new cut right here. And there's only one option. So we would use A to C. But there's a problem here. A to C was originally considered in that first cut. And this statement is saying that no matter what, if an edge was not part of the lightest edge, it was not the lightest edge of a cut, it cannot be part of the MST. But in this case, it was, because it was the only option to get to C. So therefore, this statement is false. And you can use this counterexample on the right to prove that. Cool. Let's keep going to part H. If an edge E is the lightest edge connected to a vertex S, it must be a part of the shortest path tree from vertex S. So let's think about this one a little bit more. So the important thing to note is that we want to show that Dijkstra's and shortest path is a two-way street, right? So let's create an example here. Let's say S goes to a bunch of other stuff, blah, 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 and it ends up going to T. And the thing is that, let's say that this edge right here is part of the shortest path to get from S to T. I'm going to draw an arrow to show that. And that edge would actually go both ways because, well, assuming it's undirected, we would want to find the same if it's part included when we want to go the other way from T to S. And the thing is that if we tried to use a larger weight, it would still have the same effect where that edge would not be part of the shortest path tree. And we would want to use this exact same edges basically if we want to create a path from S to T and vice versa from T to S, because it is the lightest edge. And the only way to get to S or get from S is using that edge. And especially if that's considered part of the path, the shortest path.